Hi, I'm Michael. Thank you for tuning into our paper. In this work, we will lay out how to formally describe Gaussian processes over vector fields on manifolds, taking account of differential geometric issues that arrive and characterizing all possible kernels that can be used in this setting. We also provide a quick and simple method for computing these kernels in practice and show how to use typical Gaussian process tools such as inducing points and random Fourier features in this setting. We provide some illustrative example problems, and we release an easy to extend codebase for using this methodology with your favorite manifolds. This work was done in collaboration with all the wonderful people you can see at the bottom of the slide. As an example, consider a very simplistic model of the wind on the Earth, with only a single layer of wind tangential to the Earth's surface. Imagine that we only get partial observations of real-time wind speeds, for example via an orbiting satellite. In order to infer wind speeds away from the observations, we might want to use a Gaussian process in order to have an accurate uncertainty calibration about our interpolations. With only Euclidean vector value kernels available to us, we might naively unwrap the sphere into a 2D plane and apply our Gaussian process on this space. As an example of what such a kernel might look like, a Euclidean Matern 3/2 kernel with no correlation between the north-south and east-west components of the wind, we can see the mean inference in grey arrows and the determinant of the pointwise posterior variance in colour. Unfortunately, such a naive method causes significant issues. Putting our inference back on the sphere, these issues become obvious. It does not respect the original distances over the sphere, causing warped inference, for example at the poles, and it leaves a discontinuous seam in the inference at the line where we cut the sphere in order to unwrap it. Clearly, we don't want either of these things in our inference. We therefore want an approach that will respect the inherent geometry of the manifold we are considering. But how do we do this? It is not immediately obvious how to construct a Gaussian process over the vector fields on manifolds, as in general we cannot represent a vector field as a function from the manifold into Rn. Our answer, however, is to take the manifold and embed it into higher dimension Euclidean space. In Euclidean space, we can represent a vector field as the functions from the manifold to Rn. We therefore define a Gaussian process on the manifold in Euclidean space, and then project this Gaussian process onto the tangent space of the manifold. This operation preserves the Gaussian nature of the process, and therefore defines a Gaussian process on the tangent space of the manifold, and this is independent of the choice of basis we make to represent the tangent vectors on the manifold. While initially this choice of embedding might seem arbitrary, we can show that any choice of embedding in theory can produce any permissible vector field kernel. If we now change our kernel from the incorrect Euclidean parameterization to our projected kernels, we see that we get much more sensible looking inference. Wrapping this inference back onto the sphere, we can see that the seam in the inference and the warping of the space has disappeared. Our approach allows us to tackle any manifold, however. The only ingredients we need are a scalar kernel on the manifold, which are well known, and an embedding of the manifold into higher dimension Euclidean space. Other such examples might include the torus, or more exotic manifolds like the Klein bottle. Thank you for listening. For more technical details on the construction, more example applications, or for any questions about the code, please come see us at the poster session.